afternoon, friends. We have come to the last lecture, and that is a brief introduction to lateral directional perturbed equation of motion for stability analysis, in particular for dynamic stability analysis. You are now aware how we derive perturbed equation of motion for longitudinal case. What was done? We picked the equations of motion, one u direction, w direction, and a pitching moment equations. And then we introduced small perturbation, and then we did the simplification, assuming that it's a small perturbation, and at a steady state some conditions are true, are automatically satisfied, and also product of two perturbed quantities are negligible enough, and we neglected them. And we got equations of motion. And then we have different steps, like how do I model perturbed aerodynamic force, especially Fx and Fz. For that, we derived a mechanism. Some steps were shown to you. And finally, got a matrix. And when you took the determinant equal to 0, which was like its characteristic equation, we found equation in the form as4 plus bsq plus cs square plus ds plus e equal to 0. And then we found out the roots. And from there, we try to interpret the short period mode and the phugoid mode and try to find out their natural frequencies and damping ratio. Okay? We'll be doing the similar thing for lateral directional case, but with the difference. Please understand one thing. By the way, first of all, let us understand that when I say lateral motion means motion about x-axis, and right wing going down is the positive bank. Okay? And directional is right wing going back this way. Okay? So lateral is right wing going down, and this is right wing going like this when I'm flying in this direction. So these are the two modes are generally coupled. For simple reason, you understand, if I have given a roll disturbance like this, then you could see that the lift here will be more compared to this. That is because this is taking a bank, and as soon as the lift here is more, the drag here will be more. It will not only try to bank like this, try to also yaw like this, right? So similar thing is true for the opposite case. So we say lateral and directional case are coupled, right? And that is why we have taken this equation. This is the motion along the y direction, and what was y? If I recall, y direction was, this is x, this is y, and this is z. Right? So this is the motion along y direction. This is the Ix p dot. This is the rolling moment equation about x-axis, and this is about z-axis. Okay? So these are the three equations we will be picking up and try to introduce perturbation. And as we did last time for longitudinal case, it is very simple. V will be written as V1 at steady state plus V. U will be written as U1 plus small u. And here we will assume that there may not be much change in the u. Okay? But if it doesn't matter, even if you put this u, you will find that all will be taken care in terms of small perturbation, and w equal to w1 plus small w. Like this, we will be substituting here, and then by doing this substitution and exactly following whatever you have followed for longitudinal case, you will get perturbed equation of motion as m v dot plus u1r is equal to mg phi cos theta 1 plus fy. Similarly, I will get ixx p dot minus ixz r dot is equal to q1 sb into cl, and izz r dot minus ixz p dot equal to q sb into cn. Please come back here. If you see on the right hand side, when I write fay, it is the aerodynamic force along the y direction, and fty is the propulsive force, which for our case we have neglected this, because we understand if I could do this with only fay, la, and na, I can extend this by adding additional term, right? So we have taken this to be 0 or not considered. Second thing, in this perturbed equation of motion, this is perturbed equation of motion, lateral directional case. In this, what is V? V is the perturbed velocity along the y direction. What is R? It is the yaw rate, right, about the z direction, perturbed quantity. So P is also perturbed. All these are perturbed quantity. And what is Fy here? Fy will be simply Qs into Cy, right? Okay, half rho V square S into Cy is the force coefficient. Similarly, here it is rolling moment, perturbed rolling moment. So Qsb into Cl is perturbed yawing moment, Qsb into Cn. You know by now that Cl means rolling moment coefficient it is defined as rolling moment divided by half rho V square S into B. Please note that for directional and lateral case, the non-dimensional length conventionally used is the span, not the chord like we use in longitudinal case. Okay? So this is the perturbed equation of motion. So before I go detail into it, please understand this is just to give you a glance of it. Okay? We'll need to have a separate 10 hours course on dynamic stability because it's an exhaustive course. So I thought I'll complete this in a nutshell so that you get some interest and you find that the treatment is nowhere different than the longitudinal case. Okay? Now here, if you see Fy, where I have for Fy I have Cy, and similarly here there is a Cl, which is I write it Cl, I write it Cn. Let me erase this Fy. If I write it here, if I now no more write Fy for your understanding, Qs Cy. As long as you understand these are perturbed forces and perturbed rolling moment and yawing moment, I have no problem. So Cy will be function of beta. Let me write this P R delta A and delta R minimum. There are other functionality will be there for a complicated airplane, but for a normal airplane, I can write it like this. And I'll explain you how this assumption is okay. Let us take this airplane, okay? And you know, this is the x direction, this is the y direction, okay? I am writing Cy, the side force coefficient function of beta, which is obvious. The airplane is flying like this. If wind is coming in this direction, so there is a positive beta. There is a vertical tail that will give a force in this direction. So you have Cy because of beta. Is it clear or not? Let's say this is the beta. The vertical tail is there, so force will be generated along negative y direction. So Cy is function of beta. Now the question is Cy function of P? So let us see, we are trying to visualize whether Cy is function of P or not. What is P? P is roll rate, right wing going down like this. Please note down, as the right wing is going down, this vertical tail is also going down. Okay? So it is pushing the air in this direction. So it will also experience a force in this direction. Okay? A second thing you should also understand, as it is rotating, rolling with P, so there is a relative air speed, this vertical tail will see, that will be P into this distance at whatever point I am saying the velocity, and it is moving forward, so it will actually give a beta. So you could see from simple common sense that if it is rolling like this, the vertical tail will be pushing the air this way, so it will also experience a force in the negative y direction. So we agree it is function of P also. Now for R, what is R? R is the yaw rate. Yaw rate is, what is the yaw rate? It is like this, that is right wing going back. Now you could see as it is doing like this vertical tail is also pushing the air in this direction, so it will experience a force in this direction. So again, because of yaw rate, there will be a force experienced by the airplane in the y direction. So Cy indeed will be function of R. And for delta R, it is obvious. If I deflect the rudder like this, there will be force in the Cy direction and the y direction. So Cy will be function of delta R. As far as delta A is concerned, you can neglect as far as Cy is concerned, this will be very, very small. But primary will be P, beta, P, R, and delta R. And as you understand, if there is a Cy, there will be a rolling moment and Young moment as well, because after all, primary contributor to Cy is the vertical tail. So for example, if I want to investigate whether there will be a rolling moment because of beta or not, see, if there is a beta, it's a vertical tail, so the force will act in this direction, and the force into the distance of offset from the center line will give a rolling moment, right? So there will be a rolling moment because of beta, and also you know that if there is a high wing, there will be a CL beta negative. If there is sweep, there is CL beta negative. All those things we have understood. What about P? If you see, if I roll the airplane like this, so this wing will be seeing additional angle of attack here. And so there will be a force in this direction, and that will give a rolling moment in the opposite direction, right? It's of damping nature. So CL also will be a function of P. CL also will be a function of R. You could see that if I put the airplane to a yaw rate like this vertical tail will be pushing air in this direction, so it will experience a force in this direction, and this force into this distance will give a rolling moment. So CL is also function of R, and you know, see anyway, delta A, the aileron naturally, rolling moment will be function of aileron, and rolling moment is function of delta R. That also you understand. Similarly, you can extend that understanding for Cn in the similar direction. So as long as you understand that Cy, Cl, and Cn will be function of all these motion variable and control variables, for me the life is simpler. I can write the right-hand side. Let me take one example. I write m v dot plus u1r. This is the perturbed equation of motion. Is equal to mg phi cos theta 1 plus qs into cy. So for qs into cy, I write qs into cy beta into beta, because I know Cy is function of beta P R delta R. Let's say this. Okay, so I write Cy beta into beta plus Cy P into Pb by 2v 2u1. That you understand now why Pv by 2u1, because if I write Cyp into P, P is dimensional. So I have to make it non-dimensional. Same thing we did for the longitudinal case also for Q and alpha dot. So I write like this. For every rate, I like this, Cyr into Rb by 2u1 plus Cy delta A into delta A plus Cy delta R into delta R. Although we neglect this many times, but for completion, let me write delta A also. So this is what? This is basically, I am to write this here for this. So now, if I divide every side by m, then I can get a neat equation of the form which you will like. Let me write that neat equation: v dot plus u1r equal to g phi cos theta 1, okay, plus y beta into beta plus yp into p plus y r into r plus y delta A into delta A plus y delta R into delta R. And it goes without saying, what is this y beta? Y beta will be qs Cy beta divided by m. That's all, which we have done similar thing for longitudinal case also. Similarly, I'll get equation P dot minus A1R, let me write this, R dot is equal to L beta into beta, or let me write neater form. First equation is V dot plus U1R is equal to G phi cos theta 1 plus Y beta into beta plus Yp into P plus Yr into R plus Y delta A into delta A plus Y delta R into delta R. Similarly, I can write P dot minus A1r dot equal to L beta into beta plus LP into P plus LR into R plus L delta A into delta A plus L delta R into delta R. Similarly, R dot minus B1 into P dot is equal to N beta into beta plus NP into P plus NR into R plus N delta A into delta A plus N delta R into delta R. Where you could see from the understanding, and if you derive the expression, you will find that A1 is nothing but, just for simplification, it is Ixz by Ixx, and B1 is Ixz divided by Izz. These are a matter of doing it on a piece of paper, but as I told you, this is my last lecture, and I just want to give you a glimpse of the lateral directional approach. So you could see that it is a similar thing as we did for longitudinal case. So what was the next step? Next step, we take Laplace transform everywhere, all the three equations. And also remember that beta is V by U1, and also remember R is equal to psi dot. So if we take Laplace transform here, so for V dot, what will be that Laplace transform? For V dot, what I will do first, I add V dot equal to U1 beta dot by using this expression. Right, now I take Laplace transform. So after, if I take Laplace transform of V dot, which is equal to Laplace transform of U1 beta dot, which is equal to U1 S beta of S. As simple as that. Similarly, if I take Laplace transform of R, it will be nothing but S psi of S. These two things we have to do here. And finally, when you take the Laplace transform and try to write in a matrix form and try to see what is the characteristic equation, then you will get the matrix as, write it for you just for completion, SU1 minus Y beta. Don't get upset seeing so many expressions. You need to derive it once. But the purpose of this last lecture is just to give you an idea. Make sure that this is nothing very difficult. You have to only follow a procedure, and mechanically it will happen. So minus L beta S square minus LPS, and here it is minus S square A1, and then you have minus N beta and minus S square plus B1 S square B1 square B1 plus NPS, then S square minus SNR. So this determinant equal to 0 will be the characteristic equation. And here you should note that we have already used those fact that Laplace transform R is S psi of S. And if I now take the determinant equal to 0, and I will get equation of the form, one will be x equal to 0, another will be AS4 plus BS cube plus CS square plus DS plus E equal to 0. You will get this. S equal to 0 is a neutral stability type. You can understand airplane whether it is going like this, going like this, going like this. As far as psi is concerned, it is not sensitive, right? For it, it's all same thing. Why I'm going like this or going like this, because it depends upon the relative speed. Okay, so that's why this is taken out. But this is the characteristic equation. And again here, as we did for longitudinal case, we will have a condition. First condition will be A, B, C, D, E, all should be greater than 0. And there is a second condition. And this condition to be satisfied, as we have done for longitudinal case, to ensure that that the no root is in the right hand side of the imaginary and real plane. Then it will become unstable. So here also interestingly, you will see if I see the expression of E, which I have not derived here, but you can do yourself, nothing great if you take the determinant here, you will find E is something like this, G cos theta 1 to LP NR minus N beta LR. So condition of E greater than 0 is this, right? This is the expression of E you will get if I expand this determinant and write it in this form. This is extremely important. So let's say theta 1 is 0, so anyway this is positive number. The condition is LP NR minus N beta LR greater than 0. As we have seen for longitudinal case that E greater than 0 had a special meaning, in this case also E greater than 0 has a special meaning. You will see that if E is not greater than 0, that is if this condition is not satisfied, then the airplane is likely to go into spiral divergence. What is a spiral divergence? See, suppose the airplane is like this, and because of there is some disturbance of bank, as it banks, it starts side slipping. As it side slips, it turns like this. As it turns like this, the velocity of the left wing increases, again it banks. So it goes like this, unless and until this condition is satisfied. Okay? So this is very, very important to avoid spiral divergence. Okay. Now, if we try to solve this equation in a lateral directional mode, you will find typically for most of the airplane, you will find there are three types of distinct routes. One is slowly convergent, which is what we call the spiral mode, which I explained to you. Number two, we'll find very fast or highly convergent first order, this is called the roll mode. And third one is slowly damped oscillatory mode. Just I will explain you in a very simplistic manner. Spiral mode you have understood. The highly convergent, that you understand that because there is a huge wing, right? If there is a disturbance in the bank, so this wing will give a lot of damping. It will try to come back, right? Okay. A lot of damping comes from the wing, and that is why it is highly convergent, right? The damping is very, very high with the presence of the wing, and that is the roll mode. And third one is slowly damped oscillatory mode. It is typically we call Dutch roll mode or Dutch roll oscillation. Dutch roll oscillation. It is typically, it does like this. It will be doing like this and moving like this as well as doing like this. One motion is like this, another is doing this combination of these two motion, the Dutch roll mode. So the airplane in the lateral directional case can get excited primarily in either of these mode or a combination of this mode, right? And that is why for a designer, he needs to know what are the natural frequency, what are the time period of time to double, time to half. Similarly for here, how much time it takes to go from one bank angle to another bank angle, and this then it is what is oscillation, natural frequency of Dutch roll mode to design the handling qualities of an airplane. Okay? I told you that I will give you a very short, brief introduction for lateral directional case, and knowing very well, it takes at least 10 lectures to make you understand, make all of us understand, but we have decided this dynamic stability part will take a separate 10 hours course, just to give you an idea, and it goes without saying, please get a first feel for this. Do not worry too much about exam and everything from this part at least. Okay? Thank you very much. I hope you have enjoyed. It has a lot of expressions and all, but you cannot help. We have to bear with this, and if you have any problem, do write me a mail. Thank you very much.